And the lecture slides are on Moodle now. You'll also notice that there's a link to the lab recording of Bob's concise coding conventions. And you'll notice there's the preview of the coursework and the preview of the source code. This is actually going to be the actual source code. So it's not just a preview anymore. So this is coursework source code. And we're getting questions about the coursework, which is really great. That means people are looking at it, thinking about it, strategizing, and starting. What I would suggest is that everybody brings their questions about the coursework to the lab on next week. So next week's lab will be starting the coursework actually. The lab content integrates with the coursework. So I think that's a great opportunity, and you can ask the teaching assistants for help. And that will be a great learning experience. You'll also notice that Pierre sent an announcement out about the coursework. And we've set up a new channel on Moodle to discuss coursework questions. So basically look for a channel called Coursework Questions. Post your coursework related questions there, and we will try to answer them as quickly as possible. And please read the questions that have already been asked before you post yours to avoid duplication. So it'll really be essentially a group learning experience. And yes, it will be really educational. Okay. So let's talk about hierarchies. If anybody's looking very carefully, the king is with us. King Kenny is there. He's waiting also for the lecture. And he's looking forward to the hierarchies. So we started the hierarchies last time. I don't know why I love this topic, but I do. And I guess one of the reasons I love this topic is because once you get good at designing the hierarchies, the implementation is easier. Your software implementation is easier. You create more reusable code. Your software development process gets easier. And I don't know, like there's something, you see the benefits of the hierarchies and it's really enjoyable. I really actually enjoy this topic. And I enjoy incorporating hierarchies into my software. I remember incorporating these great hierarchies into my PhD software, and I just really enjoyed it. I guess hierarchies really, they create some order out of this chaotic source code. So we started to talk about hierarchies last time, and we won't repeat all of the things I said last time. A typical hierarchy graph. And we stopped at multiple inheritance. So multiple inheritance is something we try to generally avoid. And this is a huge topic, actually, the multiple inheritance topic. And you can find a lot of content dedicated to this for both the benefits and the disadvantages of multiple inheritance. But basically, the summary is multiple inheritance introduces too much complexity and too much unpredictable behavior. That's the bottom line. So that's why it's avoided, that's why it's not supported in Java. Okay, I asked everybody about Venn diagrams last time. So Venn diagrams can represent responsibilities of a class as a set. So shared responsibilities show up in a Venn diagram. So here we have a class called Selection Tool, and here we have another class called Creation Tool. And they have a set of shared responsibilities, and that's the overlapping set in the tool. That's the tool class. So these overlapping sets, in this case, it turns into a class hierarchy. So a selection tool is a kind of tool, and a creation tool is a kind of tool. Now, this is a really funny example. If we look at the next one is that multiple inheritance hierarchy we just looked at. So the next Venn diagram is this multiple inheritance hierarchy represented as a Venn diagram. And even as a Venn diagram, it is difficult to understand, I would say. So we have our matrix class, we have our string class, and we have a date class. And the shared responsibilities of string and date show up as this magnitude. Here it gets very difficult to understand. So the shared responsibilities of string and matrix show up as this parent and array. And then the shared responsibilities of string, array, and matrix show up as an ordered collection and an index collection. So it is difficult to read. So you can even see that representing multiple inheritance in a diagram, like a Venn diagram, is complicated and not trivial to understand. Oh, magnitude. That's a good question. If you have a vector, so a vector is something with multiple components, right? A vector quantity has a magnitude and direction. So, like, if I'm pointing this way, there's a direction there, and it has two components. It has an x component and a y component. You add the x component and the y component together, and you have a direction. The magnitude is the length of that vector. So that's what a magnitude is. It's a length. You can also think of speed. So if you're driving your car, you have a direction and a magnitude. The direction corresponds to like east, west, south, north, and then the speed, which is something like 55 miles per hour, is the magnitude, right? So basically what we're seeing here is each one of these ellipses represents a class. That's what each one of these ellipses represents, right? So here we have the class ordered collection. It's in a rectangle here, but in this Venn diagram, it's inside of an ellipse. So all of the classes that are rectangles here are inside ellipses in this diagram. Right? And these, when they're overlapping, when the ellipses overlap in the Venn diagram, that represents shared responsibilities or shared behavior, right? So for the ordered collection class, it contains shared behavior and shared responsibilities of the array and the matrix and the string, for example, right? And we can see that in the diagram. Hold on, I just pressed a bad button. So let me try that again. So ordered collection shows up here. It has shared responsibilities from array, and it also contains shared responsibilities from matrix and string. So it shows up. Oh, I did it again. Pressing the wrong buttons here. Right, so it shows up. These are the shared responsibilities. These are the set of shared responsibilities represented by the class called ordered collection. And they're shared by array, string, and matrix. Right, so array is here, string, and matrix. Right, and this is the overlapping set of responsibilities between array, string, and matrix classes. And we shouldn't talk about this for very long. This is a very complicated example. This is the multiple inheritance example. Like, this is a much more reasonable example. The tool, selection tool, and creation tool, right? Selection tool and creation tool have shared responsibilities and behavior. Those are represented by their parent class called tool. And there it is, the overlapping behavior and responsibilities, or the overlapping area in the ellipses, shows up as the tool class in the Venn diagram. That's a better example to look at. This one's very complicated, and I wouldn't recommend multiple inheritance or Venn diagrams to represent multiple inheritance. Yes, I hope that helped. So here are some guidelines on building good class hierarchies. So hierarchy and Venn diagrams can help in the analysis. Here are the really important guidelines. The hierarchies, class hierarchies model the is kind of or is type of hierarchy, right? And the parents have the shared responsibilities. So we move common responsibilities or shared responsibilities as high up the hierarchy as possible. The more we can move shared responsibilities up the hierarchy, the more we can reuse code, the more we benefit from the inheritance, the properties of inheritance. Now remember, responsibilities, when you hear the word responsibility, think methods and the data that those methods need to complete their tasks, right? That's what that word responsibility means. And behavior is a set of responsibilities. And here's another important guideline. Don't allow abstract classes to inherit from concrete ones. That's a really bad design, right? And we can also eliminate non-functional classes. This is such a great topic, and I have seen hierarchies go very wrong in industry. When you get to industry, you'll find out that not everybody follows these guidelines, and you'll see some very, very unfortunate class hierarchies. So here are some of those guidelines summarized in figures, right? So class A is derived from B only if it supports all of its responsibilities. So that's what this is a class hierarchy where A is a kind of B. A is also a kind of C. Right, so A has these responsibilities, and these are shared responsibilities between A and B, and these are the shared responsibilities of A and C. Now here's a diagram where actually F and E F does not support all of the responsibilities that E does. So really this is not a proper hierarchy. And in order to make this a proper hierarchy, what we can do is we can introduce a new class. And that new class represents the shared responsibilities of E and F. So that's what this is here. So this is the class E and the class F, and then we've identified their shared responsibilities. And what we've done is we've introduced a new class called D. And that is the shared responsibilities of both E and F. And it's, in this case, it's an abstract class, right? Yes, the lecture is being recorded right now. Yes. So it should be fine. And I hope that you guys look at these lectures, these lecture recordings. It would be really great if you do. Some of the material we talk about will be featured in job interviews. So if you have a job interview for a developer position, they're going to ask you questions like, how do you define polymorphism? What is encapsulation? Can you draw a class hierarchy for me? You will get a lot of these concepts in job interviews where you're really nervous and you're sweating and you're breathing heavy. I could give a separate lecture. Actually, I've given a lecture on job interviews and job interview preparation. You can find it on my YouTube channel if you do a search for it. If anybody's interested, let me know. I can put a link to that somewhere, like either on Moodle, for example. Okay, so moving common responsibilities up the hierarchy, we factor common responsibilities as high up the hierarchy as makes sense, right? If a set of classes support a common responsibility, they inherit it from a common parent, right? Design as many abstract classes as possible. This is likely to result in the maximum design simplification, design sharing, and code sharing. It's also very likely to make the system more extensible, where later improvements are likely to be more easily integrated. If you have a class hierarchy already existing, it's so easy to add a child onto that hierarchy and just, for example, implement one new method and then inherit the rest of the methods. It's just so smooth and easy. It really makes the software development process very efficient. Decision criteria for creating abstract classes can involve speculation on possible future extensions and modifications. You can also think of that as performing a walkthrough on your software to see how your class design looks when it's confronted with a walkthrough. And one responsibility is enough to justify one abstract class. In order for the hierarchy to make the most sense, each parent requires 2 or more children, right? Generally speaking, you wouldn't want a hierarchy with only one parent and one child unless you're very confident that the future of that hierarchy is going to add more children. Yes. Yes, please remind me to put a link to the job interviews lecture on Moodle. If I can remember, I will, well, I'll make a note of it right now, actually. If I put a link to the job interviews lecture on Moodle, Somebody has to watch it. So I'll be watching the counter to make sure somebody watches it. So here's an example of designing class hierarchies. Here we have our old drawing editor example. So the drawing editor is a program that you use to draw figures, right? For example, this figure would be nice to use a drawing editor for. Here we have a parent class called Drawing Element, and it has 5 children: text element, line element, ellipse element, rectangle element, and group element. Right? If you have a figure, if you're drawing figures, you want the ability to add text to the figures. You want the ability to draw lines, like straight lines. You want the ability to draw ellipses. You want the ability to draw rectangles. And you also want the ability to make groups of shapes. So you can select like 4 shapes, group them together, and then expand them or shrink them or move them around together or make them all red. If we look carefully here, line, ellipse, and rectangle all have some things in common, right? Because they're all composed of edges. So we can add a responsibility called line style to those 3 classes, right? If you have an edge, you can have a solid edge, you can have a directed edge, you can have a dashed edge, you can have a two-way edge, and those can all be encapsulated in another class called line style. That's a shared responsibility, but it's not shared by text and group. So text is different, and group, they don't have those properties, that responsibility. So it cannot be assigned to drawing element. We can't put that responsibility into drawing element, but we can create a new abstract class that encapsulates the line style responsibility. And that's what this looks like. So the revised hierarchy now has the drawing element still at the top, 3 child classes: text element, linear element, and group element. And linear element encapsulates the line style, and it has 3 children: line element, ellipse element, and rectangle element. Does anybody remember what this red square means in the top left-hand corner of the class? Anybody remember? Is anybody awake? Yes, abstract class. Well done. Jin Ying. Well done. So people are awake. Blood, yes, blood as well. Okay, now look. Ellipse and rectangle also have a fill style attribute that is not shared by lines. So look, ellipse and rectangles, those are polygons. Polygons have an area, right? A line element does not have any area, it's just a length. So we can take the area responsibility and put it in a new class. So here's the revised class hierarchy again. We have our 3 children, but we've now introduced a new class called filled element, and it has this responsibility for defining the fill style of polygons, right? Polygons, you can put things inside polygons. You can give them different colors, you can give them different textures, you can do different things to them that you can't do with other with lines, for example. So we put those shared responsibility in filled elements. Okay, so we mentioned that abstract classes should not inherit from concrete classes. That's what this diagram down on the left is looking like, right? So we have a class A that's abstract, but it's inheriting from a concrete class C. This is not good design. Abstract class behavior should be implementation independent. So in this case, class A's behavior depends on class C. And that's not the idea behind it. That's not a good idea for an abstract class. Remember, this is abstract class, it's not another concrete class. Concrete class behavior may be implementation dependent, right? So if A was concrete, it would be better, right? It wouldn't be perfect because it's only one parent or one child, but it would not violate that rule. This characterization is violated if an abstract class inherits from a concrete one. So in order to fix this, we can introduce a new class, a new abstract class A2, and it encapsulates the shared behavior of class C and class A. So if they have any shared behavior or any shared responsibilities, they can be moved up to a new abstract class, and then these two children both inherit from the new parent. And that solves two problems, right? It makes the parent class abstract, and we no longer have an abstract class inheriting from a concrete class, and we have a parent with two children. So the biggest advantage, well, one of the biggest advantages of the abstract classes, somebody else might have a different answer for this, is it defines, well, I can think of two big advantages, but one is it defines shared behavior. That's the short answer. So it encapsulates shared behavior. So what does that mean? It encapsulates a set of responsibilities that all the child objects need to support. And that means a set of methods. So it encapsulates a set of methods that all have a common purpose that all the children need to implement, right? Can anybody think of a very common use case for this? There's a very, very common use case for interface classes. Oh, I just can't. For abstract classes. I just said the answer by accident. So abstract classes are very common when you want to implement interfaces. Interface protocol. So interfaces, you can also think of them as communication protocols. So if you want to define a communication protocol that a set of classes need to support, an abstract class or an interface is a great way to do that. This is a very, very common use case for abstract classes. I hope that answers that question. So what's the difference between an interface and an abstract class? When would you use one or the other? Very good question. So abstract, it's only the terminology. This book, the book we're getting this material from, the object-oriented design, uses the word abstract class. So it's a class with a set of defined responsibilities, but no implementations. The same is true about an interface class. So they're the same, actually. It's just the terminology. Java uses interface terminology, interface class terminology, and Wurfsprach does not. So in the Wurfsprach is the surname of the first author of this book. So sometimes I'm saying the author's name. In the Wurfsprach world, you could have an interface class that has a concrete method, a method with an implementation in it. In Java terminology, that's not possible. You cannot have an abstract class or an interface class with any implementation. That's against the rules. So I hope that makes sense. We are recording the lecture, So you can rewind, so to speak, in the future and listen to my answer again, and maybe it makes sense. Or you can ask the question again in the future. So classes that add no new functionality are normally eliminated. Remember, we're actually talking about the object-oriented design software process, where we go from the requirement specification to the implementation. So that's defining objects and classes, defining responsibilities, assigning responsibilities to objects and classes, then defining the collaborations, identifying collaborations. This is the step on hierarchies, right? Note that a class can have no new responsibilities but still add functionality. Responsibilities represent only public services. I think I've mentioned this before. Responsibilities are inherited by children but assigned to parent. What just happened? But if a child implements the parent responsibility in a different way, then it adds functionality. So that's an example of polymorphism. I do not think abstract classes in Java can have an implementation. If you want to implement an abstract class, or if you want to provide an implementation for an abstract class in Java, you inherit from that class, and then you add the implementation. So I hope that clarifies it. You create a child, that child extends the abstract class, and then you add the implementation. I hope that makes sense. Okay, we have a pop quiz, and everybody has to answer this before we go on. We have two hierarchies here. We did coursework where we implemented some methods in an abstract class in year 1. Good, good, that's very good. So pop quiz for the entire class. We have two hierarchies here. One on the left, where the top is the unit square, the parent is the unit square, and then the child is square, and then the other child is rectangle. That's on the left. And then we have another hierarchy on the right, where rectangle is at the top, square is in the middle again, and unit square is at the bottom. Now, the quiz is, which hierarchy is better? That's the quiz. So I want everybody to think about that for a few seconds. The king is thinking about that. He's really looking forward to the answers here. So basically, I will put the answers here. So left, I'm going to put left and right. If you think the hierarchy on the left is better, put a thumbs up on the left in the chat. If you think the hierarchy on the right is better, put a thumbs up on the right in the chat. There should be a right here, right. I'm trying to add the right option onto the chat, but it doesn't seem to be where. Oh, there it goes. It's just a delay. Sorry about that. There's a delay, and now the right is there twice. It's there 3 times now. This is a quiz that I give every time I teach this class. And it's a really good quiz, and it's really important, I would say, because I see this problem in real life and industry. People having trouble defining their hierarchies, having difficulties. So one of these illustrates a common error that you will find in industry when you go there. So it would be good to have a few more votes. So theoretically there are 250 people in this class. No pun intended. I can give everybody a hint. The answer is staring at you on the slide. Okay, so we have, it looks like 51 votes for left and 18 votes for right. Now, I hope everybody remembers the guidelines on defining good hierarchies. These are class hierarchies, and they model the is kind of or is type of hierarchy. Now let's look at this from the natural language perspective. We have here unit square. If we want to apply that logic to the left, we have square is a kind of unit square. And then rectangle is a kind of square. Does that make sense? The answer is no, that does not make sense. Square is not a type of unit square, and rectangle is not a type of square. So it's actually the one on the right. A square is a kind of rectangle, and a unit square is a kind of square. So it's actually the one on the right. And why do so many people get confused with this? I think the answer, I'm not 100% sure, but I think the answer is the complexity. Somehow people look at hierarchies and they think that complexity increases as you go down the hierarchy. So here on the left we have unit square, which is the simplest. We have square, which is not as simple as a unit square, and then we have rectangle, which is more complicated than a square. But that's not what class hierarchies model. Class hierarchies are not modeling complexity. There's nothing that says child is more complex than parent, and child is more complex than parent. That's not what we're modeling here. So we're modeling this is kind of responsibility or is type of responsibility. So that answers this question. Square is a kind of rectangle. It's a special kind of rectangle where every side is the same. And then unit square is a special kind of square where every edge is a unit length. So yeah, that the answer is the one on the right. And get ready for job interview questions on that kind of, you know, you could easily have a job interview question on hierarchies. So I have seen this go wrong in industry. I have seen developers get confused. They somehow have this idea in their head that hierarchies model complexity, but that's not what they're modeling actually. That doesn't mean it's impossible for a child to be more complicated than a parent, but that's not what they're modeling actually. Okay, so that's what we have on hierarchies. Any questions about hierarchies? Somebody's saying Moodle is down. Well, I think that Moodle won't be down forever, so it should be coming up again. I can check and see if my Moodle is working. Oh yeah, Moodle is down. I'm sure it's a temporary thing. Okay, let's have a preview at the Subsystems lecture for the next 5 minutes, and then we're going to take a break. So this is the last, it's the second to last stage in the transition from requirement specification to implementation. So if we take a step back, we have our initial design phase, which identifies classes, responsibilities, and collaborations. The second stage was analyze the hierarchies and identify contracts, the patterns of communication. Now we want to add another layer on top of this, which is the subsystems. So simplify patterns of communication, simplifying the application, making it easier to understand and modify. We identify subsystems, and we do so by introducing good interfaces to subsystems and classes. So we're going to look at collaboration graphs and subsystem cards. And by the way, a forward reference, the design patterns, the software design patterns, is really heavily based around subsystems. When we talk about design patterns, you're going to see a lot of different subsystems in those design patterns. Yes, I will upload the slides on the subsystems during the break. Yeah. So what's the difference between a collaboration and a contract? There is no difference between a collaboration and a contract. We're using them synonymously in this lecture. You could say that a contract is a documented collaboration. Like it's a collaboration that's been identified and then documented. But basically I'm using them essentially interchangeably in these lectures. Good question. So collaboration graphs represent the flow of information in the system, and I've said this before, this is the biggest challenge with object-oriented design, is trying to understand how the program is executed, what the flow of control looks like, and what the flow of information looks like. This is really a huge challenge with object-oriented design. So information and control flow occurs dynamically during runtime. And in order to understand the overall design, we want a static representation of all the paths in which information can flow. This is what UML is trying to achieve, by the way. UML is trying to come up with a way to draw software that shows the patterns of communication, right? So collaboration graphs include classes and their hierarchies, contracts, a set of cohesive responsibilities and collaborations. So here we have a visual representation of a collaboration. So a collaboration graph class can be represented visually, right? A collaboration graph represents classes and class hierarchies using a nested representation. So here we have a class hierarchy, right? Selection tool is a kind of tool, and creation tool is a kind of tool. This is a class hierarchy, right? There's an abstract class at the top. This is that same class hierarchy, but now it's called a collaboration graph, right? This rectangle that represents tool and the two children called selection tool and creation tool. That's a so-called nested representation of the same hierarchy. And if you think that's confusing, I agree with you. It is confusing, especially when you start mixing these two together in the same type of diagram. I prefer to keep the class hierarchy diagrams completely separate from collaboration graphs. That's my personal preference. But I see that sometimes these two representations are mixed together in UML. I don't think it's a good idea, but I wasn't one of the UML committee members. Okay, so I think what we'll do is we'll take a 10-minute break. And yeah, we'll come back in 10 minutes. I will try to upload the slides on subsystems. Yeah. Okay, let's take a 10-minute break.